Hi, this talk is about EG surface electrodes. It is the second of a three-part series about surface EG electrodes. The objectives of this talk are to explain what makes a good surface EG electrode and the physics behind good and bad surface EG electrodes. I will conduct this talk in a question and answer style. I recommend you to pause the flick on each question, read it, answer it, and only after you have done so to continue rolling. Here goes the first question. All types of surface EG electrodes are the same. A, true, B, false. Surface EG electrodes, as you can gather from the objectives of this talk, can be good and can be bad. Let us start talking about the good ones. Good surface EG electrodes have a stable electrode potential and transmit information from the scalp to the EG machine and from the EG machine to the scalp with high fidelity. The good surface EG electrode, if presented, let's for simplicity's sake say with two negative charges in the form of ions at the disk, interact with them and deliver an equal value of charges, let's say 2 electrons at the other end. Good electrodes also conduct charges in the other direction. So, if presented with 2 electrons at the pin, 2 negative ions will be discharged at the disk. We call this quality, that is the ability to carry charges in both directions, reversibility. So good electrodes are said to be reversible. We can say the same about positive charges going from the disk to the pin and from the pin to the disk. We call this quality, that is the quality to handle negative as well as positive charges with high fidelity, non-polarizable. Bad electrodes, on the other hand, if presented with 2 negative ions at the disk, may not interact with them at all, or if they do, yield no electrons at the other end, or an inappropriate amount of charges in the form of electrons at the other end. And the same can be said when presented with positive ions at the disk. There may be no interaction, or if they interact, yield a dissimilar value at the pin. And the same happens if presented with positive charges at the level of the pin. So, in good electrodes, the charges going in are equal to the charges going out, regardless of the direction. While with bad electrodes, what goes in is not equal as to what goes out. So, the answer to this question is B. Next question. What makes a surface EG electrode good to record direct and alternating currents? A. To have a stable electrode potential. B. To be non-polarizable. C. To have a long time constant. D. All of the above. It stems from this question that EG tracing, when recorded by a good EG machine, will differ if the surface electrodes are good or bad. Good surface electrodes produce tracing with little baseline drifts because they have a steady electrode potential in each electrode and their electrical potentials are balanced among all electrodes. Bad surface electrodes have big baseline drifts because they have an unstable electrode potential. That is, they are not steady in each electrode, nor are they balanced among all electrodes. Good electrodes faithfully reproduce negative and positive electrical currents, as well as low frequency and high frequency activities because they conduct electricity in both directions with high fidelity. Bad electrodes do not faithfully reproduce negative and positive electrical currents, nor do they faithfully reproduce low frequency or high frequency activities because they are irreversible and polarizable. Good electrodes faithfully record amplitude because they have a long time constant. Bad electrodes unfaithfully record amplitude because they have a short time constant. So the answer to this question is B, all of the above. The next question is: the main culprit in the production of baseline drift is the space function of the electrical double layer. A, battery; B, transducer; C, low frequency filter; D, frequency dependent filter. As you can remember from the prior talk about surface electrodes, the reactions that take place in the electrolyte-electrode interface renders it the function of a battery, a transducer, a low frequency filter, and a frequency dependent filter. Well, the main culprit in the production of baseline drift is the battery function of the electrical double layer. So the answer to this question is A. Next question: electrode potentials cannot be generated unless the electrode is connected to the scalp. A, true; B, false. This figure has been introduced during the first surface EEG electrode talk. You can find it in YouTube by going to Israel Alfonso and then selecting the appropriate talk. As you can see in it, a representation of the brain and the skull is pointed by the arrow. The skull is represented here by the white circle. Then the skin, the gel, and the electrode are represented. The positive and negative circles indicate positive and negative charges in the skin, the gel, and the electrode. But the main point of this figure in the context of this question is the presence of the electrical double layer. The electrical double layer, as you know, develops at the electrolyte-electrode interface. The electrolyte-electrode interface in this figure is represented under the yellow bracket. The electrical double layer renders the electrode the function of a battery, thus producing an electrode potential. In the next figure, I will introduce a similar figure, but this time lacking the figurine representing the brain, the skull, and the skin. I remove these structures while maintaining the other components to convey the fact that the electrical double layer remains despite the removal of the brain, the skull, and the skin. Indicates that the battery function and the electrode potential are the result of the interaction between the gel and the electrode. So the answer to this question is B. Next question. The literature draws a stiff distinction between bias potentials and electrode potentials, A true, B false. It would be nice if all neurophysiologists would agree on the meaning of electrode potentials and bias potentials. Most neurophysiologists that I have heard talking about these terms, few in number, I would have to say, do not draw an ironclad distinction between them. My own preference is to use the term electrode potential for the battery effect of the electrolyte-electrode interface, when it is measured directly and experimentally at the level of the electrolyte-electrode interface, as you can see presented in this frame, and to restrict the term bias potential to the battery effect when recorded not from one electrode, but from two EEG electrodes connected to an amplifier, thus forming a derivation as we do during EEG recording. Hence, when used in this fashion, bias potential reflect the difference in electrode potentials of two connected electrodes and is influenced by the common rejection mode and the amplifier input impedance of the EEG equipment being used. In the next frame, I will show a sample of this bias potential obtained in this fashion. The arrow points to a recording from two electrodes held in the air with no gel. Since it can hardly be seen, I enlarged the recording in this frame. As you can see, no significant amount of activity is present. In this frame, you can see what happens when gel is applied. Again, the arrow points to the recording, but since it is too small, I enlarged it in this frame. You can see a significant amount of electrical activity. You can more easily see the difference tracing in this frame. This frame compares the recording in the same situation, except for no gel in the top tracing, gel on the midline, on the middle tracing, and gel and human contact in the bottom tracing. It is from my own heart. Viewed in mathematical terms, bias potential can be thought of as the subtraction of the voltage of the electrode potential, here represented as A, and B. The execution of this operation is represented here as C. C is the bias potential for this pair of electrodes. So, as I said, it would be nice if the terms electrode potentials and bias potentials be consistently used in the literature, but the reality is that they are not. And very often, you have to guess, based by the tone of the sentence, which of the two is being addressed. So, the answer to this question is false. The literature does not draw a stiff distinction between bias potentials and electrode potentials. Next question, steady bias potentials, if balance between electrodes do not produce artifact, A true, B false. I like to address this question by going back to the figure I just showed you before. In this frame, I have represented bias potentials as a mathematical operation. Let's say that the electrode potential for A is 3 volts and the electrode potential for B is 3 volts. So the execution of this subtraction is 0. So if the electrode potential are steady within each electrode and balanced among all electrodes, that is, if the bias potential are steady and balanced, they will not produce an artifact. On the other hand, not being this the case, that is, if the subtraction does not yield 0, but any other positive or negative number, then the bias potential is unsteady, unbalanced, or both, and they are likely to produce artifacts. So the answer to this question is A, but it is important to recognize that if the steady and balanced bias potential are very high, it may overwhelm the amplifier impedance and common rejection mode of the EEG equipment, and artifacts will be produced in such an event. The next question is, balanced steady bias electrode potentials can cause amplifier block when switching to a new montage. A, true, B, false. The answer to this question is true. This was often present in the past with all EEG machines with limited input impedance and common rejection mode, but does not often occur in the digital age. The next question is, steady bias electrode potentials, if unbalanced, will produce artifact. A, true, B, false. As we have explained, bias potential exists in two forms: balanced and steady, which do not produce artifact usually, and not steady and unbalanced potentials, which produce artifact. So the answer is A, steady bias potential, if unbalanced, produce artifacts. Next question is, a bias potential results when the difference in the properties of two electrodes cause an imbalance in the net electrode-electrolyte ionic transfer. True or false? The answer is true. I hope you got this one right. The wording of this question is literally taken out of a book. I do not remember which, but I vaguely remember seeing a similar question in one of my old boards. The next question is, steady bias potentials are worse than unsteady bias potentials. A, true, B, false. With a steady balanced potential you can live with, since most of the time the component of the EEG machine can correct it, but we cannot say the same about unsteady ones. So the answer is B. Next question. Which of the following functions is the most frequent cause of electrode artifacts? A, battery, B, transducer, C, low frequency filter, D, frequency dependent filter. Of the four electrode functions that we have spoken about, the battery function is the most critical in the production of electrode artifacts. I will further elaborate on this point by introducing a familiar figure. You have seen this figure multiple times. The main point I want to make at this time concerns the electrical double layer, to which I will refer for this frame as EDL, using the initial letters of each word. So when the EDL is disturbed due to an intrinsic phenomena such as a change in consistency of the gel, for example, as it occurs when the gel dries, or it is disturbed by non-desirable contraction of a muscle or pulsation of an artery, electrical artifacts may occur. So the answer to this question is A. Next question is, all of the following decreases the likelihood of unacceptable bias potential except A, use pure metals, B, use the same type of electrodes, C, use clean electrodes, D, use silver chloride electrodes. The causes of not steady or unbalanced bias potentials are many. Here I will mention a few. An unequal amount of gel between two coupled electrodes. In this and in the following frames, the gel will be represented in yellow and the skin in tan color. No gel on one of the electrodes, as to be resting on the scalp while the other having a normal amount of gel. Couple electrodes at different temperature, like it happens when one electrode is close to an outlet of an air conditioner while the other is not. Coupling electrodes with one good and clean disc surface to one with a dirty or broken surface. Using electrodes of different materials, or coupling an electrode with a broken pin with another one with a normal pin. So the answer to this question is A. Metals need to be the same in all electrodes, regardless whether they are pure or not. Next question is, which of the following steps can be taken to minimize the battery function effect on the AG recording? A. Same metal, size, and age of electrodes. B. High amplifier input impedance. C. High common rejection mode. D. All of the above. We already looked at this figure as causes of bias potential. Every possible step should be taken to eliminate these sources of bias potentials. But in addition, it is also important to consider the built-in EG safeguards that prevent electrode artifacts. Most importantly, high amplifier input impedance and high common rejection mode. So the answer is B, all of the above. The next question is, which of the following electrode functions is most critically involved in the production of excessively polarized electrodes? A. Battery. B. Transducer. C. Lower frequency filter. D. All of the above. The most critical electrolyte-electrode interface function involved in the production of excessive polarization is the transducer function. I am sure that you can recognize all the components in this figure, hence I will not point them out to you, but I'd like you to spend a few seconds viewing them. I reintroduce this figure at this point to remind you of the mode in which charges are conducted through electrode scalp junctions. Charges are carried through the skin and gel as ionic charges. These ionic charges at the level of the electrical double layer are transformed into electrons. The electrons are then transported through the wire to the EEG machine. Thus, the behavior of the electrical double layer confers the electrolyte-electrode interface the function of a transducer. This process also occurs in the reverse, where charges carried by electrons from the machine through the electrode wire reach the electrical double layer and are transformed into ionic charges. Then the ionic charges travel back through the gel and the skin towards the brain. What I have just explained to you is what happens during good EEG recordings. So charges move and are transformed at the electrical double layer. But as we know, not all electrodes are good. Bad electrodes produce a dysfunctional electrical double layer. This may occur when positive charges accumulate. When positive charges are accumulated in the electrical double layer, the electrical double layer will attract and allow the transfer of negative charges, but will not allow positive charges to go through. If, on the other hand, the charges that accumulate are negative charges, positive charges will go through, but negative charges will not. So the answer to this question is B. Next question. Which of the following transducer model can be labeled reversible? A, just with positive charges. B, just with negative charges. C, with negative and positive charges. I hope you find the answer to this question obvious. I added this clip from the paper by Cooper written in 1963 because I remember seeing a question based on these statements on one of my boards. I've taken the neurophysiology exam, counting certification and recertification 3 times, and they do not get any easier. Anyway, read this paragraph carefully. The gist of the paragraph is that the electrode potential only changes if it is exposed to voltage above or below the voltage value of the existing electrode potential. Hence, it is the voltage value of the electrode potential at the electrical double layer that determines what activity will be recorded. So the answer to this question is C. What I hope this drawing convey is that transport positive and negative charges in an appropriate direction will occur once the threshold is met. The next question is, polarized electrodes means bad electrodes in the EEG literature. A, true. B, false. I'd like you to read this paragraph again carefully. My interpretation of it is that in order for current to go through, some polarization must be present. I base this assumption on the principle that one of the characteristics of the electrical double layer is to produce electrode potential. By definition, an electrode potential can only develop if different charges are facing each other and have a net difference of charges. I also like for you to pause the flick at this junction and read this paragraph from Misuli's book. I think that it implies that polarized and non-reversible are synonymous terms and as such define a bad electrode. Another interesting point in this paragraph is that in non-reversible electrodes, the electrolyte-electrode interface, here referred as junction, develops the function of a diode plus a capacitor. I have introduced in this frame a new paragraph from another book. The book is Fundamentals of EEG Technology. This paragraph talks about extreme polarization transforming the electrode into a diode. It also talks about the distortion on alternative current that will be brought about by the transformation of the resistive qualities of the EEG electrode into a diode. I have also added in this new frame another paragraph. This paragraph is from Cooper's EEG Technology book. Please read it. It breaks out 3 very important points. The first point is that high resistance impedes high fidelity. The second point is that this author uses the term polarized to label electrodes with high resistance. And the third point is the fact that such electrodes with high resistance behave like capacitors, not permitting the recording of steady potentials, which I think it is referring to direct current and slow changing potentials. Finally, this is the last paragraph I am going to ask you to read. The reason I include this paragraph here is because it equates low resistance at the level of the electrical double layer with non-polar non-polarized or reversible electrodes. In the lower part of this frame, I have introduced the model of the electrical circuit that we already discussed during the prior talk about electrodes. I am introducing it here to illustrate the conclusion I have gathered from reading all these different books regarding polarization and surface EDL electrodes. I will label all its components, so if you have forgotten them, you do not have to go back and read them again. The arrow points to the brain and the skull. Next is the skin. Next, the resistance to ionic conductance of the gel. The structure in dark orange represents the electrolyte electrode interface. In it, in one leg, we see the symbol for a capacitor. In the other leg, we see the resistor, implying a straight resistance of the electrolyte electrode interface, followed by a capacitor and a resistor. These two elements, that is, the capacitor and the resistor, represent Warburg impedance. The green line represents the outgoing segment of the circuit, and the gray line with the symbol for a capacitor implies straight capacitance. That is, the unavoidable capacitance produced by circulating electricity. So, what are the conclusions I have reached from reading a significant amount of conflicting literature on the subject? There are three. The first is that some polarization has to be present in all electrodes connected to the scalp, or just simply connected to the gel, just by the nature of the interaction between the electrolyte electrode at the interface. This polarization is the cause of the battery effect of the electrical double layer, and is needed in order to conduct charges. I have represented the conduction of charges by adding the partially transparent yellow lines. I have made the lines going through the resistor, Warburg impedance leg of the circuit thicker to indicate that more current goes through this leg of the circuit than through any other. Also note, the arrow in this frame is going towards the machine. In this new frame, all is the same except for the arrow pointing to the scalp. I have done this to indicate the reversibility of the process. The second conclusion is that too much polarization is bad. Too much polarization is bad because in this situation, most of the current will not travel through the resistor leg of the parallel circuit, but through the capacitor leg. I again have represented this by the thickness of the yellow lines. The consequence of this is that since the capacitor prevents the passage of slow waves more than the passage of fast waves, the fidelity of the circuit will be affected. This occurs when current is moving towards the ED machine and when current is going in the opposite direction. The third conclusion is that in the face of extreme polarization, current flows become very abnormal, to the point that if we are to create an electrical circuit to explain the electrical behavior of the electrical double layer in these circumstances, we would have to substitute the resistive leg of the parallel circuit by a diode. In this model, current will initially be allowed to go in one direction, relatively unimpeded by the diode, but will not be allowed to return through the diode leg of the parallel circuit, and all will be conducted as straight current or will go through the capacitor leg of the electrolyte electrode interface circuit. If this occurs, there will be the predicted loss of fidelity. So the answer to this question that I believe will be found correct in an exam setting is A. I think this is the expected answer because the term polarized seems in most textbooks to be equated to non-reversible, and that both are defined as a marker of bad surface electrodes. But just for your understanding, remember all that I have just said. The next question is the electrical double layer of non-polarizable or reversible electrodes have very large capacitance value and very small resistance and wall break impedance. A true, B false. As I pointed out previously, when I told you the conclusions I have come up with from reviewing the conflicting literature on the subject, the term non-polarizable and reversible surface EEG is used to refer to a surface EEG with normal electrical double layer at the electrolyte electrode interface. The fact that some polarization is present even in the electrical double layer of this surface EEG is usually not taken into account when using this label. The answer to this question is A. The next question is the electrical double layer of polarizable or non-reversible electrodes has very large resistance and Warburg impedance and very small capacitance value. A true, B false. As you can see, this question is just the opposite of the prior question. I think that you would find the answer obvious. Nevertheless, I will reinforce this concept in the following frames. So, in the literature, the term polarized surface EEG is used for electrodes with high resistance, thus relying on the capacitant leg of the circuit for the conduction of current, with the expected decreased fidelity by impeding the passage of a slow activity, or with extreme polarization, with transformation of the resistive leg of the parallel circuit into a diode which will allow current in one direction but not in the other direction. In such a case, the electricity is forced to go through the capacitance leg of the parallel circuit or as a stray capacitance. So the answer to this question is A. The next question is the main culprit in the production of short time constant is the dash function of the electrical double layer. A battery, B transducer, C low frequency filter, D frequency dependent filter. Of the four functions of the electrical double layer, which by now you have seen many times, the one that contributes the most to the production of a short time constant is the low frequency filter function. So the answer to this question is C. Next question: what characteristic must an electrode have in order for it to have a long time constant? A, to have a low Faradic resistance. B, to divert current to the capacitor. C, to be of pure silver. D, to be made of pure gold. I'd like to start considering this question by reintroducing in this frame a smaller version of the electrical circuit representing the skin and the surface EEG electrode. It is the same figure I have introduced in the past, but this time I am excluding the brain. On the left side, I am representing a pulse of direct current given at the level of the skin and sustained for a period of time. You can see it as a white line. The double-headed arrow indicates time in seconds. Such a current in a perfect electrode with perfect connections would conduct current only through the resistive and wire break impedance leg of the electrical circuit. No current would be conducted through the capacitor leg nor through the straight capacitance circuit. I have represented current as a semi-transparent yellow line as I have done in the past. The arrow head indicates the direction of the current. Such an electrode and connection would yield at the level of the pin of the electrode a carbon copy with a smaller amplitude of the current introduced at the level of the skin. In the example that I have just introduced, the electrical double layer has a higher resistance, so some of the current injected at the skin will go through the capacitor leg of the circuit. This current is here represented by a thin yellow line. Conduction of current through the capacitor, as you know, blocks slow wave current more than it does fast wave current, thus producing a drop in amplitude that reaches about 70% of its original height in a little bit longer than 1 second. This is called the time constant. So we can say that the time constant of this circuit that we have just introduced is a bit longer than 1 second. In this frame, I have introduced a new example. In this example, the resistance is higher, thus less current will go through the resistor leg of the parallel circuit and more current will travel through the capacitors. This phenomenon will provoke an even sooner drop in voltage. In this frame, I have introduced a fourth example. I do so to indicate that as the resistance of a circuit increases, less current travels through that leg of the circuit and more through the capacitor leg. And in the last example, at the bottom of the frame, the only difference is that the current is now also traveling through the straight capacitance component of the circuit. This occurs because the resistance through the resistive leg of the circuit is very high and the capacitor is also overwhelmed. Therefore, there's nothing else for the current to do but to travel through the straight capacitance. The result is that the drop in voltage occurs much earlier. Please take a moment to look at this frame. Notice how the less current travels through the resistive leg of the circuit, the sooner the drop occurs. So, to summarize this concept, the terms non-polarizable electrode, reversible electrode, or inert electrode are used to describe good EEG electrodes. Good electrodes are good because most of the current travels easily via the resistant leg of the electrolyte electrode interface. The word easy is there to emphasize that the conduction through this leg of the circuit is very high and does so in both directions. Polarized or non-reversible electrodes are terms used to indicate bad electrodes. They are bad electrodes because they either conduct current mostly through the capacitance leg of the circuit or the resistance wall breaker impedance leg becomes a diode. In this frame, I am introducing an example of the first possibility, that is, when most current travels through the capacitor or via a capacitor and a diode due to low conductivity. As you know, a diode only allows conduction of electricity in one direction. So the answer to this question is A. For an electrode to have a long time constant, it must have a low Faradic resistance. The next question is, the best way to minimize the low frequency filtering property of the electrical double layer is to increase the current going through the resistor. A true, B false. Take a moment again to see this frame. Follow the drawings from the top to the bottom, and as you can see, the more current travels through the capacitor, the shorter is the time constant. Seen from the other point of view, the better the conduction through the resistor, the longer the time constant. So the answer to this question is A. The next question is, recording eye movements is an easy way to determine time constant of different electrodes. A true, B false. The eyeball can be thought of as a battery with a positive charge towards the cornea. If we decide to monitor eye movements by placing one electrode lateral to the left eye and to enter that electrode through the G1 element of the amplifier, and to place another electrode at the location of A2 and to enter that electrode through the G2 element of the amplifier, when the patient is looking straight ahead and the electrodes are made of silver chloride, we will get a pretty much straight line. If at this point the patient looks to the left and sustains the gaze there, the recording will show a sudden drop, reflecting the positivity at electrode 1, and the line will remain at the same level and straight as long as the gaze is sustained. If at this point the patient is asked to look straight ahead again, the recording will go up and level at the same position it was at the beginning. If the patient is now asked to look to the right and sustain the gaze, the tracing would go up, reflecting the negativity created by the displacement of the cornea, and will remain there as long as the gaze is sustained. If we ask then the patient to look straight ahead, the recording will, as you expect, go down and stay there. If instead of using silver chloride electrodes, we use a gold surface electrode, the intervals between the vertical lines will not be sustained because gold electrodes have a shorter time constant than silver chloride electrodes. If instead of using gold, now we decide to use stainless steel needles, the inability to sustain the voltage achieved after the initial deviation is even more noticeable. The reason for this is that stainless steel needles have an even shorter time constant. So the answer to this question is A. Next question. The maintenance of a similar impedance with changing frequency depends on the blank function of the electrical double layer. A. Battery. B. Transducer. C. Low frequency filter. D. Frequency dependent filter. Of the four reactions that take place at the electrical double layer, maintenance of a similar impedance with changing frequency depends on the frequency dependent filter function of the electrical double layer. And remember that the frequency dependent filter is explained by the mysterious Warburg impedance. So the answer to this question is D. The next question is, A good material for building an electrode would be one that has the same impedance at all frequency. A true, B false. In this frame, I want to point out the relation between frequency and impedance of different electrodes. As you can see, silver-silver chloride surface electrodes have similar impedance at 10 Hz than at 1 Hz. The same cannot be said about stainless steel sphenoidal electrodes, whose impedance at 10 Hz is relatively close to the impedance of silver chloride surface electrode, but it is much higher at 1 Hz. The difference in impedance related to frequency is even more noticeable when using platinum alloy. So the answer to this question is A. Before going to the next question, I would like to make you aware of a paper that was written in 1997 by Giddis. The title of the paper is Historical Evolution of Circuit Models for the Electrode-Electrolyte Interface. I think that is a good one to read, especially if you have the time. The next question is, charges are carried in the form of electrons between two silver-silver chloride electrodes immersed in a sodium chloride solution. A true, B false. I will approach this question by sketching and explaining a few experiments. The first experiment consists of depicting the diagram of an electrical circuit with a resistor powered by a battery. The other element present in the circuit is a switch. In this case, the switch is open. In this frame, I am introducing two electrodes touching a wire in the circuit connected to an amplifier with a writing system. And in this frame, I am introducing a stopwatch to indicate time. During the first second, the circuit is open. When the circuit is open, no current goes through. The recording will reflect this by a level straight line. At 2 seconds, when the circuit is closed, the pin will rise. While the circuit remains closed, the pin will remain at that level. When the circuit is open again, the line will go back to baseline. Then it stays at the baseline until the circuit is closed again. At this time, the pin will go up and stay there for as long as the circuit is closed. At this point, if the circuit is again open, there will be a drop in the pin, and the pin will stay at that level as long as the circuit remains open. In the bottom of this frame, you can see I have enlarged the tracing. The only reason I did this is so you can see the tracing better. The conclusion from this experiment is that current travels through a purely electron-based circuit with little distortion. The next experiment starts where the first experiment ended. This is the same circuit I showed you initially. The switch in this case is closed, so current is going through it, and this is reproduced at the level of the recording by the pen being raised. In this frame, I have removed one leg of the circuit, so creating an open circuit despite the switch being closed. Thus the pen will drop down because no current will be recorded by the electrodes attached to the amplifier. With the passage of time, the tracing will remain down as it would be expected in the absence of current. I have enlarged the tracing in this frame so we can see it better. The conclusion of this experiment is that air does not conduct electricity between two free wires. Now I will move on to the third experiment. Here we start with the same circuit as we were looking at last time. One leg of the circuit is missing, so no current is being conducted despite the switch being closed. Now we are adding to the end of the open wire two silver chloride disc electrodes. They are represented by the silver color circles. Obviously, since the two silver chloride electrodes are not connected, and air that is filling the space between the two silver chloride electrodes is a good insulator, no current will be conducted through them. Again, I have introduced a larger tracing for better appreciation. The conclusion of this experiment is that two silver chloride electrodes, when separated by air, do not conduct electricity. Now let's do a fourth experiment. In this experiment, I am going to start with an open circuit and two silver chloride electrodes. Since there is no connection between the two silver chloride electrodes, the tracing will be recording a flat line. Now I will place a bucket, here represented in yellow, and will fill the bucket with a sodium chloride solution. Once the bucket is full and both silver electrodes are immersed in the solution, the pen will rise, since a connection has been established by the sodium chloride between the silver chloride electrodes. The current will continue to flow as long as the circuit remains closed. Remember that the switch has been closed so far during this experiment. Now we open the switch, thus creating an open circuit despite the communication between the silver chloride electrodes. Once the circuit is open, no further circulation of current will occur and the tracing will go back to baseline. And it will remain at this level until the circuit is closed again. At this junction, the pen will go up because it will be reflecting the passage of electricity through the electrodes connected to the amplifiers. This state will continue until the circuit is open again. Once the circuit is open, no further current will circulate while it remains open. As I have done before, I have enlarged the tracing at the bottom so we can see it better. The conclusion of this experiment is that electricity is conducted from one silver electrode to the other silver electrode when the silver electrodes are immersed in normal saline and the switch of the circuit is closed. What we have seen in these few last frames, and the aim of telling you about all these experiments, is that the electrical charges can be conducted in the form of electrons through wires or in the form of ions through sodium chloride solution. And most importantly, that the conversion of electrical charges into ionic charges that occurred at one silver chloride electrode is mimicked by the conversion of ionic charges into electrical charges at the other silver chloride electrode. So the answer to this question is false. Charges are not carried in the form of electrons between two silver chloride electrodes immersed in a sodium chloride solution. The next question is, the perfect material for building an electrode would be one that conducts charges similar to an electrical circuit wire. True or false? In this frame, I am representing a purely electrical circuit. Here, the electrical circuit is open. Here, the electrical circuit is closed. The tracing below represents the recording made over time in a similar fashion as we had done during the first experiment I mentioned before. On the other side, I have introduced figures from the fourth experiment. As you can recall, this experiment was conducted using silver chloride electrodes submerged in a solution of sodium chloride. The arrow at the bottom is pointing to the tracing recording using these elements over time. You can see how similar it is to the pure electron circuit that is on the other side. So here I have indicated the composition of the electrode as being silver chloride. In this new frame, I have substituted the electrodes for copper. The rest is kept the same. As you can see, when you compare the recording using copper electrodes to the purely electrical circuit, there is a significant difference between the two. Now, instead of using copper electrodes, I have used pure silver electrode. Again, I have put the result of the tracing in the bottom, and as you can see, the difference between when pure silver electrode is used and when a purely electron circuit is used, there is a significant difference in the shape of the tracing. Now, instead of pure silver, I'm going to show you what happens when you use platinum. Again, the tracing will be different than the tracing that we saw when we were using purely electron circuits. You can see this reflected and pointed out by the arrow in this frame. Now, if instead of platinum we were to use pure gold, the tracing will be different from what we would get in a pure electron circuit. So the answer to this question is true. The next question is, which of the following is the best material for the construction of EEG disc electrode? A. Copper, B. Silver chloride, C. Silver, D. Gold. From our discussion regarding the prior questions, we can conclude that silver chloride is the best available material for electrodes. This is because they conduct electricity very similarly than do pure electron-driven circuits. So the answer to this question is B. Next question. Silver chloride electrodes behave like a reversible chloride electrode with silver chloride acting like a bridge. A. True, B. False. The structures listed in this frame represent the elements involved in transferring electrical activity from the scalp to the electrode wire and from the amplifier to the scalp. The rectangle below each structure lists the most common substances involved in electrical transfer. As you can see, at the level of the skin is chloride, potassium, and sodium. At the level of the gel is sodium chloride. At the level of the gel electrode interface, we find silver ions. At the external layer of the electrode, we find a thin plate of silver chloride. At the level of the electrode, we find only silver. And at the level of the wire, we find electrons. Current generated at the brain forces chloride ions from the skin to interact with sodium chloride present in the gel. The chloride ion then interacts with the silver ions and dislodges electrons from the silver that are transported to the wire. The wire carries the electrons to the amplifiers. The same occurs, but in the other direction, when electrical activity from the EEG machine is transported to the scalp. So the answer to this question is true. The next question is, which of the following electrodes offer less Faradic resistance? A. Copper, B. Gold, C. Platinum, D. Silver chloride. I am sure that by now the answer is obvious to you. Silver chloride electrodes experimentally have proven to produce a tracing very similar to a pure electrical circuit. But I will take a bit more of your time to elaborate on this answer. Of all the metals and metal compounds so far studied and in commercial use, the one that will transmit more electricity through the resistive leg of the electrolyte-electrode interface is the one that will more closely reproduce a square wave. So, as you can see, pointed by the arrow, the circuit with less resistance through the electrical double layer will reproduce a pulse of direct current best. The silver chloride electrode, in addition to a proven value experimentally, has also done so in recording regular EEG. It is true that since most of the activity studied during regular EEG is of alternating nature and as such less vulnerable to the effects of capacitance, we most of the time can get away using electrodes not made of silver chloride. But the fact remains that electrodes made of silver chloride are the best. So the answer to this question is D. The next question is, which of the following electrodes are less altered by capacitance? A. Copper, B. Gold, C. Platinum, D. Silver chloride. This question is sort of beating a dead horse. The answer is silver chloride electrodes. So the answer to this question is D. The next question is, which of the following is true about silver chloride electrodes? A. Can be mixed with any other metal electrodes in the same recording. B. Has no electrode potential. C. Do not produce a steady bias potential. D. Is a non-polarizable electrode. In this frame, you are looking at electrode potential from different metals. I have added in this frame the electrode potential for silver chloride electrode. As you can see, it is not the lowest or the highest. Silver chloride electrodes should not be mixed with electrodes of other materials. Silver chloride electrodes, like all other electrodes, produce bias potentials, but if balanced and steady, do not lead to artifacts in the recording. Silver chloride electrodes are non-polarizable. This quality makes them mandatory to be used when recording direct current and preferable when recording alternating current. So the answer to this question is D. They are non-polarizable electrodes. The next question is, which of the following materials has more baseline shift? A, copper, B, silver chloride, C, silver, D, gold. When copper is used experimentally, as it is depicted in this figure, or in real recordings, there is significant drift of the baseline, as you can see. When silver chloride is used, there is minimal to no drift at all, experimentally and in real recordings. When silver is used, there is minimal to no drift too. And when gold is used, there is also minimal to no drift. So the answer to this question is A. Next question. The choice of surface EDL electrode used depends only on the electrical quality of the metal. A, true, B, false. The answer to this question is B, false. More than the electrical qualities of the metal goes into deciding what electrode to use. Next question. What issues should you consider when selecting surface electrodes? A, cost, B, resistant to oxidation and corrosion, C, harmless to living tissue, D, all of the above. The answer to this question is D, all of the above. The next question is, which of the following statements is not true? A, electrode wires should be less than 1 meter. B, passage of direct current to measure resistance while the disc is attached to the scalp should be avoided. C, wires should be made a strand cable separated only at both ends. D, wires should be separated from each other throughout their extension. It is better to bunch electrodes wire in a strand and to only let them separate at both ends. It is better because the magnetic field created by current through each winded wire cancel each other. Thus, stranded electrodes are better than electrodes that run in the same direction and are not wind around each other. So the answer is D. All the other options are true. Take a second to read them over, please. Next question. Which of the following increases the possibility of polarizing an electrode while conducting an EEG in a patient? A, changing from 9 to 10 millimeters electrodes. B, changing a silver chloride electrode for a gold one. C, measuring electrode resistance. D, measuring electrode impedance. In this frame, I am representing the measuring of resistance in an electrode. This is done by applying a pulse of direct current with the electrode disconnected from the patient and before the gel has been applied to the electrode. If the pulse of direct current is given while the electrode is connected to the patient or with the gel, polarization may occur. As you know, polarization should be avoided. Impedance is measured by providing a pulse of alternating current, usually of 10 Hz, but could be between 10 and 30 Hz while electrodes are connected to the patient. So the answer to this question is C. The next question is, which of the following is not true regarding electrodes? A. Electrodes offer little impedance for high frequency waves. B. Electrodes are best if 4 to 10 millimeters. C. Electrodes are best when polarizable. D. Silver chloride electrodes should not be used intracranially. As you can see in this frame that I have shown you before, other than for silver chloride electrodes, all other electrodes shown in this frame have more impedance for low frequency wave than for high frequency waves. The size of surface EEG electrodes should be from 4 to 10 millimeters. Silver chloride electrodes cannot be used intracranially, and polarized electrodes can lead to production of artifacts. So the answer to this question is C. Next question. Which of the following electrodes have MRI compatibility? A. Gold. B. Chloride silver electrodes. C. Steel electrodes. D. Platinum electrodes. The answer is the metal that you're seeing in this frame, which is platinum. So the answer to this question is D. So, in conclusion, good surface EEG electrodes are so because 1. They have little baseline drift thanks to a stable electrode potential. 2. They faithfully record currents thanks to being reversible and non-polarizable. 3. They faithfully record amplitudes thanks to having a long time constant. It is these qualities that allows the good surface EEG electrode to transmit fast frequency waves, slow frequency waves, and square waves with high fidelity. Silver chloride electrodes, when coupled with a sodium chloride base gel, behave like a chlorine electrode and are the best available electrodes currently in the market. Thank you.